All right, welcome back. This is the end of week 3. So you'll recall at the beginning of week 0, we played around with this, with a whole bunch of our staff up on the stage. And the goal there was to consider just how efficiently, how effectively we could solve a fairly mundane problem of just looking up someone like Mike Smith in this phone book. And recall that one of the first passes at it involved, well, start at the beginning, turn to the second page, turn to the third page, ... 1,000 some odd pages later, bam, we happen upon Mike Smith. But of course, almost everyone, except Jason, as I recall up here, went at this phone book by tearing it first in half, and then in half, and then in half, and then in half again. And that algorithm, or that procedure, we decided was, in theory, much, much faster than this sort of old school start at the beginning, go to the end, and stop as soon as you find Mike Smith. And just to refresh some jargon, if we said that the old school naive but very correct approach was linear in nature, and that we were just kind of walking along a straight line from left to right in the phone book, how did we describe the smarter approach that the CAs and TFs took? Right, so it was logarithmic, right? So sort of maybe a flashback to high school math at this moment, but logarithmic, in short, was better. And we'll actually feel what we mean by better today and beyond, because today we put aside C entirely for just a bit. No new syntax, nothing new scary today, but we finally start to deliver on this syllabus's promise that 50 is ultimately about teaching you to think more carefully and solve problems more efficiently and more effectively. So with that said, recall this. No need to stand up this time. This particular algorithm, which was actually very similar in spirit to that phone book example. In the phone book example, again, the linear approach was left to right, but the logarithmic approach, the divide and conquer approach, was to start in the middle and then repeat, tearing half of the problem away again and again. So you went from 100% to 50% to 25% to 12.5% and so forth. It was really a whittling down of that phone book. This algorithm too, recall that first day we all stood up and we had each of you pair off with the person next to you, and then one of you sat down, but the other kept both your number plus their number. And so if you continue that logic of having everyone stand, then half people sit, half people sit, half people sit, but you never throw away any of the numbers that are in your head because you just hand your number off to the person still standing. In theory, at the end of that algorithm, we should have had just one person standing, and his or her number should have been the collective count in the room, because everyone, recall, started at 1. Now that's a bit of a cheat, that approach, in that it was not so much a more efficient algorithm per se. It was really leveraging more than one CPU, right? If each of us is sort of the brains of that algorithm, well, we threw like 400, 500 CPUs at that problem and ran the algorithm in parallel. But we'll see when you only have just one CPU, one core, one brain inside of your own computer, you can still leverage this idea of divide and conquer and ultimately get much, much faster and smarter implementations. Now, rather than use everyone in the room here, thought we'd pick on those of you in the orchestra section, just those of you here on the ground floor. Otherwise, this isn't too easy. So if just you folks would humor me for just a moment and execute step 1 here, let's see if we can't find within this orchestra section the tallest person among you. And this should be easy if you're all standing on flat ground. All right? Execute. OK, need to do a side-by-side comparison. Oh, all right. And what's your name again? Renzo. So Renzo is indeed the tallest person in the orchestra section today. Congratulations. All right. So first of all, it didn't go unnoticed. There was a whole lot of opting out in the back section there of the orchestra. But that's OK. So Renzo was the tallest. And consider, in theory, how fast this algorithm should have been. If everyone stood up, then half of you sat down, half of you, half of you, half of you. So again, if we start with, say, not just maybe 50, 60, 70 people here, but instead start with 1,000 people, we then got down to, say, 500, and then 250, and then 125. If you can kind of think about these numbers, they really start to shrink and shrink and shrink pretty quickly. In fact, if we extrapolate like we did in week 0, if we had, crazy thing, 4 billion people sitting in just the orchestra section today, how many iterations would there have been of this three-step algorithm? So only 32, right? It would be a kind of a mess. But of course, with just 32 steps, and by 32 we get that from, you can divide 4 billion in half again and again and again, a total of 32 times. I mean, that's kind of a powerful thing. Even if you had 4 billion people here, after just 32 rounds of this, everyone would have sat down except one person, and that person would be standing like Renzo with the total amount. Now, what's the contrast here, right? That's kind of powerful. It's kind of nice that we're leveraging all these brains. What would be the alternative, right? If I did it sort of old-fashioned style, I would start down here, and I would say, would you mind standing up for just a moment? All right, so I'm going to compare these two fellows here. And of course, this is a very close tie. So we're going to break the tie randomly. So I'll say, Joe, you stay standing. Go ahead and sit down. Now what do I do again? Well, I now walk down to the rest of the aisle. I find someone else. I compare those two. One of them sits down. I move on to the next, onto the next, onto the next. But all this while, I'm remembering who is the tallest person I've seen thus far. So I kind of remember that person or drag them along with me. But at the end of the day, that algorithm is still something linear. I have to make some n-1 comparisons if there's n of you, and I have to compare all of you, one person against all of you potentially to find the tallest, so that would actually be much slower. If we did have some 60 or so people here, that would take 60 steps, whereas yours would have taken 60 to 30 to 15 to 7.5 to 4 to 2 to 8, like 7 or 8 steps to do that same thing in this size group. So thank you, Joe. So linear is obviously a bit slower. So how can we now leverage these sort of commonsensical ideas that we're using in this human context to actually now leverage them in more powerful contexts? Well, first, what's really the goal? So let's just kind of plot arbitrarily, like you might on a graphing calculator or Excel or on a piece of paper, what these things look like. So if we very generically say that this chart represents on the x-axis the size of some problem, and size we measure typically numerically. We usually call it n as a generic variable. And the size of the problem that we've been playing with here are the number of people in this room. So 60 in this case, a few hundred in the total case, so n equals that value. So the farther out you go over here, the more people there are to count in the algorithm, the more input there is. Now on the y-axis here, the time to solve, that's just a generic way of saying how many steps are there going to be, how many seconds, how many minutes is it going to take to actually execute this algorithm given this many people. So if we plotted here in red a straight line, straight implying linear. So if we had n people in this room, as the size of the problem grows from left to right, well, the amount of time it would take for me to count you back in the first week, or for me to find the tallest person in here manually by comparing every person against, comparing pairs of people again and again until I find the tallest, well, every time you add another person to the orchestra section, it's going to take me one more step. If 100 more people come in, sit down in the orchestra, 100 more steps. So it's a one-to-one, a linear relationship. Now, what did I do in week 0 as an optimization of counting everyone in the room? It was kind of slow to say 1, 2, 3, 4, 5. So what was the obvious marginal improvement? All right, so count in pairs. So 2 people at once, 2, 4, 6, 8, 10, 12, 14, and so forth. And just verbally, you can hear how the speed has obviously increased. It's twice that. But graphically, it's really just the same shape of a line. It just happens to be a little lower, right? Because you can actually have more people, but it's going to take less time if you look up the y-axis, obviously because you're counting them twice as many at a time. But when you all counted yourselves, or in this case, found the tallest person in just the orchestra section, well, the shape of that graph is much more powerfully curved and almost flat like this, whereby if we graph how much time it takes to count the number of people in the mezzanine or find the tallest person, the number of people in the theater or the tallest person in the orchestra, well, you get this shape instead. And why is that? Well, if we literally doubled the number of people in this orchestra section, suppose there are 60 more people come in, they sit down, how many more steps does my algorithm take if I'm actually using something like divide and conquer, this parallelism? Just 1. And that's kind of the powerful idea. You can double the size of the problem, and I barely bat an eye at it because I can absorb that problem by just executing one more step. But by contrast, the linear algorithms, if I was doing it manually, 1, 2, 3, that would take 60 more steps to count 60 people. So the goal here ultimately is not going to be to count simple things like this, but try, and most every time we start implementing new problems and solving more interesting challenges in the p-sets, is to try to figure out, well, can I get away with something linear? It's quick, it's easy, I know for loops and while loops. Or can I actually make something that's smarter than that, that's more efficient than that, that's better designed? And if you consider the applications here, right? We've talked about the 6 degrees of Kevin Bacon example, and just asking sort of very reasonable questions like, who are my friends of friends on Facebook? That is not an easy question to answer as the size of your social network grows because of the multiplying effects of having your 1,000 friends times their 1,000 friends and so forth. That graph's actually going to look much more different. In fact, kind of take a mental image of these 2 straight lines and then this curved green line, green meaning good here, and if we actually zoom out and consider other possible algorithms, those 3 colored lines have now kind of flattened themselves out on the right-hand side there. And what you see plotted here now are numbers like, well, suppose your algorithm was n squared. In other words, if you've got n people, it takes n squared steps. 10 people, 100 steps. Well, if it's n cubed, it's even bigger. If we zoom out further, though, you can see that there's at least one type of algorithm we probably want to avoid throughout life, and that's anything that looks like this. This is what we would generally call an exponential algorithm, where you take some constant number like 2 and then raise that to some variable number like n here. And we'll put this into context before long. There are some very famous and some very common problems that potentially fall into that bucket. But you can see just from the shape of this graph, if you just to have an input of size 60 people, 60 something, and my God, it takes 200,000 units of time, I mean, that's a lot compared to anything that's down there. Now, you've all been sectioning for this class and other classes, and can you just think about, Harvard has in the fall semester like a few thousand classes of varying sizes, and we have a few hundred rooms probably, and there's a few hours in the day, 9 to 6-ish, that classes might be held in, and there's some finite number of faculty. So there's all of these various inputs. And if you just start to think about now, I've got a few thousand times this many rooms times this many students, all of whom have this many constraints, the problem of scheduling people or resources or rooms or classes is actually one of those problems that tends to fall in the 2 to the n bucket, at least if implemented poorly. FAS's sectioning tool, which you used for this class and probably for some of your other classes, if you actually Google around, you can find the algorithm that they use, and it's actually disclaimed as not being optimal. It is not the perfect solution. It will not maximize all of your happiness across campus, because doing so would actually take a ridiculous amount of time. You would essentially have to compare every possible person's possible maximum happiness given a current schedule, then compare it against everyone else's optimum, and then figure out from that exactly who we should put in which class, which section, with which TF. It just takes too long. Certainly if you have many classes, all of whom are trying to section at once, so they optimize. Maybe there's a bit of randomness. And so with randomness, with optimization, kind of cutting corners, the program like that can say, you probably got your first or second or third choice, but if you kind of added up all of your happiness, if you could kind of quantize it somehow, odds are most of you are not perfectly happy right now with your section assignments. But that's sort of the nature of these kinds of problems. So let's just slap some jargon on one thing, just so we can express things a little more succinctly later. In programming, in computer science more generally, computer scientists have some shorthand notation for describing